Hi everyone. I thought I'll very briefly talk about the circuits called flipped voltage followers in this lecture. I'd already posted a document on YouTube uh, talking about flipped voltage followers and their applications in different circuits. So flipped voltage followers, as the name suggests, they are just voltage followers and which also exploit feedback to give you very low output impedances. So the term flipped voltage followers was coined in mid 2000s. I think there was a paper in 2005. That's when we started using the word popularly in literature. And after that, they have found applications in LDOs. They have found applications in low voltage differential amplifiers. Okay, and we have also been using a structure very similar to flipped voltage followers in folded cascode amplifiers, fully differential and differential to single-ended folded cascode amplifiers. I'll try to talk about each of those applications in different videos. The first lecture, I thought I'll just introduce the basic purpose and the analysis of a flipped voltage follower. So a flipped voltage follower structure consists of two transistors, which are shown here. Okay, it is a source follower. The main device is a source follower device. Input is at the gate, output here is at the source. The difference is there is another device which is placed in negative feedback around this source follower device. And by doing this, we can get very low output impedances. Okay, so how do we get that, and how to analyze the circuit intuitively and rigorously using control theory is what we will discuss in this lecture. So before that, very briefly about source followers. So a source follower or a voltage follower, we have the one that we know is a common drain amplifier. Input is at the gate, output is here at the source, and generally it is biased using a constant current source. So when you bias it using a constant current source, by design you are not ensuring its DC or the drain current to change. So which means the small signal VGS or GM times VGS is supposed to be equal to 0 because the constant current is enforcing that condition. The small signal change in the current is 0. And since you are biasing this device with a finite current, the GM of the device is finite. So which means the VGS has to be 0, which means gate voltage will be equal to source voltage, or source follows the gate voltage. So which is why it's called source follower. The output impedance of a source follower is the way we find is we just open circuit the current source and look into the source terminal, ground the input that will be just approximately it's 1 by GM parallel or not, so we can say approximately 1 by GM. Okay, that's the lowest impedance that you can get using a single MOS device. And we also discussed, I would recommend you go through some of my previous lectures or any previous material on source followers. They are impedance transformers. If you have a circuit which is supposed to drive a resistive load, the thing is that the resistor tends to load the circuit. Okay, and by adding a resistor, the gain of the circuit itself might change, especially if the output impedance of the circuit is very high. So to resolve this problem, we already discussed that we introduce what we call a buffer or a voltage follower in between. So it transfers the same voltage at this point to the output as well, but at a much lower output impedance. The output impedance of a source follower will be very low. Okay, so here lower the output impedance, the better it approximates the behavior of a good voltage follower or a voltage buffer. So coming back to that, we'll see how to analyze this circuit to find its output impedance. So we just discussed that lower output impedance is good and how to do that. So a quick analysis before we go to the control loop model is that to analyze, I'll draw the circuit in a slightly different way, which is what I've shown in this figure here. And I'll draw the device 2 here, which in this fashion, and then put the device 1 in feedback. So it's going to look something like this. Okay, so now I'm looking at this node. The output node at this point is the resistance seen here. What is the output impedance at this point? So we can quickly see in open loop, let's say there was no negative feedback. then the output impedance would have just been RO2. So let's call this device 2 and this device 1. The output impedance would have just been RO2. But now there is negative feedback. In the presence of negative feedback, if you apply a test voltage Vt, what would happen is that this is like a common gate amplifier, and the DC gain of a common gate amplifier with open load, your load is infinity. Okay, it's going into the gate of the device, which is infinite impedance, is 1 plus GM1 naught. So it will be 1 plus GM1 RO1. So if you apply a test voltage at the drain, that appears as a huge amplified version at the gate of device V2. So now the drain current of this device M2 is simply 1 plus GM1 RO1 times GM2. I can times Vt. I can approximate this to GM2 times GM1 RO1 times Vt. Okay. So the output impedance is simply V by voltage by current. So you end up getting Vt divided by this value, which will be 1 by GM2 into GM1 RO1. Okay. So compare this with a common drain amplifier, conventional common drain amplifier. The output impedance was just 1 by GM. Now here it is 1 by GM multiplied by a huge factor. Okay, so we can get very low output impedances using a flipped voltage follower. Now for the voltage, as far as the voltage gain is concerned, the same principle holds. If you look at the transistor 1 here, the drain current of this transistor, which is injected at the drain terminal, doesn't change. It's constant. It's held constant. So therefore, the source voltage has to follow the gate voltage. So V0 is approximately equal to Vi. So that condition holds true. Okay. In fact, here I'm finding it for an open circuit condition, but that's how we analyze source followers also, right? If you take a source follower, we normally find its open circuit output voltage, and then we find its output impedance and model it as a Thevenin equivalent. Thevenin equivalent for a source follower will be Vi with an output impedance of 1 by GM. Okay. Now the Thevenin equivalent of a flipped voltage follower will also be Vi, but the output impedance will be much lower. It will be 1 by GM2 times 1 by GM1 RO1. So which is intrinsic gain times lower than the output impedance of a conventional source follower. Now what I'll do is I'll try to analyze the flipped voltage follower circuit using negative feedback theory. Okay, so since most of you would have gone through an introductory course on circuit design, which explains everything using negative feedback. So because there is feedback in this circuit, I thought I'll explain it using negative feedback as well. So to do that, what I'll do is we'll do the analysis for NMOS based flipped voltage follower. See, again, a flipped voltage follower consists of two transistors. So since there are two transistors and we have NMOS and PMOS, two flavors of devices that can go in as one of those two transistors, there are a total of four combinations possible, right? 2 into 2, that's totally 4 combinations. And but what we'll do is we'll analyze one of them, and the same thing will hold true for every other combination. So I'll do the NMOS only flipped voltage follower analysis, and then we'll assume that the same thing holds true for all the remaining 3 configurations as well. So I'll slightly redraw the circuit. So here I've redrawn the circuit with M1, that's the input pair Vi and output V0, and there is the device M2 which is connected this way. Okay, so I've drawn it in a negative feedback in a manner such that you can compare it with a control negative feedback control theory model. Okay, so the moment we finish the drawing equivalent model to the circuit, then the next step is to find out the open loop and closed loop gains, open loop and closed loop output impedances. Okay, so before we do that, quickly you can see that the output quantity of interest is voltage, and you're feeding the voltage back to the input. Okay, so it's a voltage feedback circuit. So ideally, you should expect the output impedance to become smaller and smaller. Okay, input impedance should become larger than its than its open loop value. Output impedance should become lower than its open loop value. And we can also compute, once you know the forward gain, you can compute the closed loop gain as well. So the first step in analyzing any negative feedback circuit is to compute its loop gain. Okay, so to compute the loop gain, we need to break the loop at some point. Okay, and then we apply a test voltage and return back to the same point and see what is the gain of the circuit. So if you see, there are two main nodes in the circuit. One is at, I'll just show the circuit here. So there are two main nodes. So this is device M1, whose drain is connected to the gate of device M2, and the drain is connected back to the source of M1. So there are two nodes here. This is one node here, and this is another node here. So I can break the circuit at any point, any of these 2 points, and find out the loop gain. Okay, and if you want to, I'd recommend you go through my previous lectures on the loop gain, how to calculate loop gain in analog circuits. I think it's in the playlist Microelectronic Circuits, lecture 79, 77 and 77A. I'd recommend you go through that. There I've spoken in detail about how to estimate or compute the loop gain of negative feedback circuits. So coming back here, I can break the loop at this point or at this point. So when I'm breaking the loop at this point, whenever you're breaking it, you should ensure that try and break the loop where the input impedance seen into one of the nodes is infinity. If you break it, then it's perfectly fine. You can just apply a test voltage and calculate the loop gains. Otherwise, you have to terminate both these inputs, both these nodes, by the impedance looking into the node itself. Okay, so that's what you need to do. So luckily, if you see at both these nodes, the impedance looking in is infinity. Why is that? Now, if I look at this node, this is a common gate amplifier. Source is at ground. Sorry, input is at ground. So it's a common gate amplifier. You're looking into the source. Since the drain is open, no current can flow here. Therefore, the impedance looking here will be infinity. Okay, and similarly, if you are looking at this node, if you are breaking the loop at, say, this node, the input impedance looking at this node will be infinity. Okay, so you don't have to worry about impedances, putting the right impedances after when you break the loop. Okay, to ensure that the loop gain is accurate, the loop gain you calculate is accurate. So you can just break the loop at either of these 2 points and compute the loop gain. So first step, I'll break it at this point, and I have to return back to this point. So which is what is connected back here. I have to return back to this point here. So the gain of the first stage will be 1 plus GM1 RO1, and the gain of the second stage will be minus GM2 RO2. So the total loop gain will be 1 plus GM1 RO1 into GM2 RO2 with a negative sign. So here the negative sign shows that it's a negatively fed back circuit. In the same way, I can break the loop at this point here and calculate the loop gain. So the gain from V1 to this node here is minus of GM2 RO2. Why is that? Even though you are connecting the drain here to the source of M1, the looking impedance into the source of M1 is infinity. So the M1 device does not load the device M2 or the common source configuration M2. So the gain will simply be minus GM2 RO2. That multiplied by 1 plus GM1 RO1 is the overall loop gain. Okay, loop gain is negative, so therefore it is negatively fed back. So this is your overall loop gain of this amplifier. The next step is to find the forward path loop gain and forward path output impedance. So I'll keep the amplifier as it is. The way I've redrawn the flipped voltage follower, I'll keep it as it is, and now try to estimate the open loop gain and open loop output impedance. So as you can see here in the circuit, to find the open loop gain, you have to ensure that the fedback quantity is 0. You have to ensure that VF is 0 here. So any negative feedback system, if you're finding the loop open loop gain, you have to ensure the quantity that is fed back is 0. Okay, so how do I do that? I'm feeding, if you look at this circuit here, previously I was feeding the drain voltage back to the source. So I have to ensure that here I have to open circuit the drain and then ensure that the fed back quantity is 0 here. Okay, and the output has to be open circuited. The feedback network should not load it. You have to just keep it open here. Okay, so once you have the circuit, ideally you should terminate the output terminal here with the impedance of the feedback network, but here there is no feedback network. You are directly feeding it into the source here, and the impedance at the source is infinity. So you can just leave it as it is. So now we have the open loop model ready. Once you have the open loop model, you can just calculate the open loop gain, and also you can calculate the output impedance. Output impedance in open loop ROL is just RO2, the output at this node. So how do you calculate the output impedance? Short circuit the input and then find the impedance at the output node. That will just be RO2 itself. And the loop gain is a cascade of two common source amplifiers. So this, in the forward path, it reduces to a cascade of two common source amplifiers. So the forward path gain is going to be minus of GM1 into RO1 times minus of GM2 into RO2. So that will be GM1 RO1 into GM2 RO2. This is your open loop or the forward path gain of this amplifier. Okay, since you're directly feeding the output V0 back at the input, beta is equal to 1. So let's not worry about beta right now. We have gotten the forward path gain and the loop gain. So now we have everything ready to calculate the closed loop voltage gain and the closed loop output impedance. Okay, we have the open loop numbers and we have to just find the closed loop number. So the closed loop numbers, you can see from the circuit, the closed loop TC gain is going to be AF by 1 plus loop gain, and the output impedance closed loop is going to be RO or open loop divided by 1 plus loop gain. That's it. So since we already have the numbers, you just have to plug it into these equations, and you end up getting the closed loop. Since the open loop gain here, the loop gain here is approximately equal to GM1 RO1 GM2 RO2, right? I can assume GM1 RO1 to be much greater than 1, and the whole product will also be much greater than 1. So I can assume this to be approximately equal to the forward path gain itself. So you get the closed loop gain as 1, and the output impedance is again RO2 here, RO2 divided by the loop gain. I can approximate it to GM1, GM2, RO1, RO2, and you get the same result, which is 1 by GM2 to GM1, RO1. This is exactly the number or the value which we got in the initial part of the analysis. If you recall, we began the discussion and we analyzed it without using feedback theory. We just used some quick KCL and KVL and the conventional analysis methods that we know. And then we found it, and it's the same value as this. So that is the output node and the input node. We said the circuit has two nodes. There is one other node which is the intermediate node. What is the node voltage Vx? So for that, again, I can use the same open loop and closed loop expressions. So the open loop value at the node of node Vx can be found by ensuring the feedback voltage is 0 in a similar way, and you end up getting Vx to be minus of GM1 RO1. That's your times Vi. That's your open loop voltage gain divided by the loop gain. You get the overall closed loop voltage gain to Vx. That will be minus of 1 by GM2 RO2. Okay, it shouldn't be surprising because if the output node voltage is approximately equal to Vi, then divided by the gain of this amplifier should be the gain of this stage. So that will be Vx should be equal to Vi upon minus of GM2 RO2. Okay, that's what you should expect. So which means Vx, the node voltage Vx is not changing much. It's changing insignificantly. The gate of the device M2 or the drain of device M1. So if you draw the flipped voltage follower, it looks something like this. The drain is fed back here. So as this input and output are changing, the change at this node voltage is very small. It's actually the change in Vi divided by GM2 RO2 with a negative sign. Okay, so if your R naught is infinity, if your MOS transistors are ideal, if your R naught is infinity, then Vx should not change at all, and V naught will be exactly equal to Vi. Okay, so this device should not see any. If your R naught is infinity, then this device provides you infinite gain. Therefore, the gate at this node should not change at all. Okay, so negative feedback ensures that these two terminals are at same AC potential. So you get this result. Okay, so I've just tried to show it here. If you assume your output impedance to be infinity, if this MOSFET R naught is infinity, you can show that the output impedance will be 0. Okay, so you can apply a test voltage Vt or a test current It and try to measure the voltage developed at this node. If your output impedance is finite, a finite voltage will be developed. So what happens to the current It if you compare it with a conventional common drain amplifier? If you apply a test current It, all the test current will flow through the MOSFET itself, and the voltage it develops at this node will be I times R, so it will be It divided by GM. The output impedance is 1 by GM, so multiply by that, you get the delta, the change in the voltage here. Okay, ideally you want it to be 0, which means change in the voltage should also be 0. Okay, here if you see in this circuit, if you inject some current at the output, that current does not flow through the source follower device. So if you see here, this M1 device is the source follower device. The current here does not flow through that. Okay, if you inject this current It, it actually flows through the device M2. M2 takes in that current, the current that you're injecting at its drain. Okay, so the gate voltage will change appropriately to take in that current. So that's one major difference between a flipped voltage follower and a source follower. If you see, for a source follower, as you change your load current, I plus IL, let's assume, here you can assume the current, I'm just changing it by delta I at the output. Okay, or you can just assume that I've put a load resistance and I'm changing my load resistor. Then the current in your source follower device itself will change. If the current in your source follower device changes, that will change your DC biasing voltage at this point as well. On the other hand, a flipped voltage follower circuit, the voltage across the voltage follower will remain constant. I can do that. So for example, let's assume I've shown here a source follower and the flipped voltage, PMOS flipped voltage source follower. So this is typically used in LDOs. A structure like this is used in LDOs. So let's say you are feeding, the source follower circuit is feeding an analog circuit, and the analog circuit's current is changing by delta I. Then we can see in a conventional source follower, the current of the source follower device itself will change by delta I. Okay, delta I units. On a flipped voltage follower structure, which I've shown here, so this is sourcing current into the analog circuit, the voltage follower. So if the current in the analog circuit increases by delta I units, that delta I flows from, this is M2 and this is M1. So this is the PMOS equivalent of our NMOS circuit. Okay, so the current in M1 remains fixed. That is fixed by I0. That is always fixed. But the current through M2 can change depending on where you connect it, how you connect it. Okay, so that's another benefit of flipped voltage follower circuit. So you can ensure that the VGS here remains constant, which is very helpful when you try to use this circuit for biasing LDOs.